Assalamu alaikum. My name is Ahmed Riahi. I'll start by introducing our second project, where we are focusing on the main two components of baseband digital communication systems, which are source coding and channel coding. Now, before jumping into these two concepts, first of all, we have to know that these two blocks are part of information theory, which is basically the study of how to represent certain quantities in a mathematical measurable way, while also showing the limit to the system's performance. Now, in order to proceed, we have to know how to measure information. And judging by the fact that information contained in a given message is inversely proportional to the probability of that message, and according to Shannon, in digital communication, we will end up with the following equation, which is I equal log 1 over P, where I is measured in bits and P is the probability of the message. Now, when it comes to source coding, the main objective is to represent the coming data with a reduced number of bits in order to have a more compact signal with reduced redundancies. For example, if we have a number of messages from a source, just as shown here, such that the messages are not equiprobable, and where the information in each message is represented as I equal log 1 over P, we can obtain the average information in the source by applying the summation of the information multiplied by their probability. And we will end up with the following equation, which is also known as the entropy. The entropy is also defined as the minimum number of bits that can be used to represent information without any losses. In fact, the entropy was proven to be the limit to any source coding method, so there is no method used that can do better. So if we calculated the entropy of a source h of m, and we use any source encoding method, the data coming will be represented in a number of bits m, such that m will always be greater than h. And if we get a value that is less than h, that would just mean that data was lost somewhere. We lost data. Moreover, if we have a source encoder that represented data in a certain way, where each message was represented in a number of bits, we can obtain the average number of bits used to represent this information, which is also the average, called the average length. And by using the following equation, we can obtain that, where n is the number of bits in a message, and p is the probability of that message. Now my colleague will move on with the.
Assalamu alaikum. My name is Husam Al Ardah, and as my teammate has just reviewed how to benchmark the performance of any source encoder with the entropy as our reference, there are two approaches on actually how to perform source encoding when reducing redundancy. The first method is fixed length source encoding. By looking at the source, we first identify the number of possible messages, which is denoted by n, without really paying attention to their probabilities. Therefore, the formula used for calculating the minimum number of bits for each message is expressed as shown in the slide, where we take the log base 2 of n. And considering this is a lossless representation, for practical reasons, the number of bits assigned to each message should be an integer, meaning the ceiling is taken from the result when applicable. However, this technique is only optimal for achieving a value close to the entropy under two conditions, and that is first, the messages are equiprobable, and second, n is an integer power of 2. Only this way can we successfully represent each message with a minimum number of bits. Moving on, the second and more reliable method in performing source encoding is known as variable source encoding, which revolves around the concept of allocating more bits for messages with less probability. The reason why more bits are assigned to them is primarily because they have higher uncertainties to them. A well-known technique for variable source encoding is known as Huffman encoding. In this example, assuming we have a source with 6 messages, the first task is to assign them in descending order of probabilities in the far left column as shown. Next, we aggregate the last 2 messages into one combined message, being the sum of their probabilities. So for this case, the messages with a probability of 0.1 and 0.08 would be combined into 0.18. Next, we arrange our new n-1 messages in descending order of probabilities in the next column, and then repeat the steps when adding the last 2 messages. This iteration goes on until we end up with 2 probabilities as shown in the far right column, being 0.57 and 0.43. After we assign each of the 2 probabilities with a unique binary value using the convention of 0 for the highest probability, we begin to work backwards. We're starting from the rightest column, we allocate a new bit every time we move to the left column and when a combined message breaks up. This iteration also repeats until we arrive to the far left column with our original messages with the assigned bits as shown in the orange box. Moving on, for the analysis, by calculating the source entropy using the expression my teammate described, we obtain a value of an average of 2.422 bits per message. For Huffman encoding, this value is slightly higher, being 2.45, which proves that despite Huffman being the optimal choice and instantaneous, it still cannot reach the source entropy in some cases. Huffman technique could have given us the source entropy, however, if we worked with the number of messages to the power of 2, such as 8. On top of that, the method of fixed length coding gave us an even larger average bits per message of a ceiling value of 3. Finally, by analyzing the tables, the trend seen is that for fixed length coding, each 6 messages are assigned a unique combination of 3 bits, where for Huffman, messages with higher probabilities are now expressed in 2 bits only, which is ultimately better.
Assalamu alaikum. My name is Mohammad Murtaza and I will be talking about the systematic linear block code. So before going into the math, we will first look at each term of the word and we'll start with the block codes. Block codes are codes where you map like k-dimensional space to n-dimensional space, and you do so using a generator matrix G on the encoder on the encoding part and a parity check matrix on the decoding part. Now, linear block codes are block codes where if you take any two valid code words and you do the XOR operation, the resultant code word will also be a valid code word, and all of three would belong to the code set. Now, systematic linear block codes are codes which are in the format that the k most significant bits are the information bits and the remaining m bits are the parity bits. Now, if we go into the math, we'll see that the information bits are information vector. They are multiplied by the generator matrix, where the generator matrix is the identity matrix appended with the parity matrix. Now the resultant code word would have length n, and it will be transmitted over the channel, and on the receiving end or in the decoding part, it is the received code word is multiplied by the H transpose, where the H matrix is the parity check matrix having the P transpose or the parity bits matrix transposed and appended with the identity matrix. The resultant of this multiplication between the code word received code word and the H transpose is called the syndrome, and we perform a check on this syndrome. If the syndrome is equal to the 0 vector, it means that no error has occurred and we just have to extract the k most significant bits, and this will be our message because it's a systematic linear block code. If the syndrome is not equal to 0, then it means that an error has occurred and the transmitter has to send that again. Now if we look at an example having where we have like 2 information bits, these are all the combinations, possible combinations are there, and these are their respective code words, and we see that for each of the valid code words the syndrome is equal to 0, and in that case the message is just the 2k in like most significant k bits. Now let's just assume that if we did not receive a valid code word, being an invalid code word being 1001, and the syndrome for it is not equal to 0, then it means that it is an invalid code word and the transmitter has to send it again. That will be for my part. My colleague will continue on.
Hello everyone, my name is Nabil Ben Ammar and I'm going to be talking about the channel coding theory and Hamming distances and weights. The objective of channel coding is to increase the reliability of the communication system through optimizing values for the 3 contradicting parameters, which are the probability error, but through decreasing it and increasing the rate of transmission and reducing the transmission power. A widely used method for channel coding involves systematic linear block codes, which consist of mapping a k-dimensional message and performing a mathematical operation to obtain n-dimensional code, which consists of many code words as an output. Before going to the circle as an example, I'll briefly explain that in the n-dimensional, we can have 2 to the power n possible values. However, we are only using 2 to the power k because we aim to achieve with this a high reliability with the least probability error with a rate as close as possible to the capacity C. This example, which showcases a circle, simplified the channel coding operation. First, we observe that the circle, which is the n-dimensional space, which is the new space after mapping the k messages, we can see the small orange dots, which are the possible values of the space, However, in our system, we want to make sure that the black points, which are the valid points, are as far as possible from each other in order to reduce the probability error. So in case there is a noise interference, a low noise, the black point will go to an invalid point, and that will make the receiver send again to the transmitter to send the information again. And in high noise, we might have a probability where it can go exactly to the valid point. Going to the Hamming weight. Hamming weight is the number of ones in any code word C in the code. So in this example, we can see that we have 4 columns, which n equal to 4. We have the examples of counting the Hamming weight for each code word. For the first one, we got 0 because there is no ones, and the second one we got 2s. So the same thing for the other 2. And we obtained the minimum Hamming weight in order to approve the SLBC. And for the Hamming distance is the different number of bit locations between any two code words. We're going to count it in this example between comparing C1 and C2. We obtain that the Hamming distance is equal to 4 because we have 2 different bits. We have 4 different bits in these 2 code words. For the minimum Hamming distance of code word C, which is between all pairs of multiple code words inside the code book, which we have to consider when looking at the properties of systematic linear block codes. We always have to have minimum distance of the of a minimum Hamming distance is equal to minimum Hamming minimum weight. Thank you. Following to my colleague will continue.
Assalamu alaikum, my name is Amr Attia. I'm going to talk about the channel coding. It contains 2 parts, limits on performance and design channel coding method. Performance of measure of channel coding depends on reliability, which measures the digital communication system using bit error rates, or the other name for it is the probability error. It has to be under transmission rate R, which why the probability of error, and the transmission rate has to be contradicting objectives which manage the signal to perform one of them and sacrifice the other as a trade-off. The channel needs a bandwidth at least as the value of the transmission rate to proceed without noise. Shannon capacity theorem. It achieves reliable communication over noisy channel as long as the transmission rate R is less than the capacity of channel given by the equation. We're gonna explain it in the next slide briefly. The channel capacity band and channel coding performance given by the equation W log 2 log to the 2 1 plus SNR is equal to the W log 2 1 plus the power over NW, which refers to the SNR as the noise of the ratio which contains the power signal over the noise. Based on Shannon's theorem, we can see that the digital communication system can be traded through 3 parameters. Probability of error decreases and the transmission rate increases and the power of the signal decreases to make the performance of the channel with high reliability of trading off. Also, there are 2 effects occur to the channel when the power increases the capacity to increase, and the other effect when the bandwidth increases, the capacitor will increase and decrease in the same time until it saturates. And the code rate is equal to the length of the input over the length of the output. Thank you.
These are all references, and that will be all. Thank you very much.